Okay, so let's begin. Good morning. And so somebody wanted to ask me a question from last lecture, so now you can ask.
So, when we said that P is equal to dl by q, del q dot, and we wrote that dq dot in terms of P and Q, so why we ignored the explicit dependence of time in the Lagrangian? I mean, shouldn't be that q dot should also be dependent on time?
That's not explicit dependence, right? That's implicit dependence through Q. So when we write something, we have a Lagrangian, which is a function of Q of t, Q dot of t, and t. So so the dependence which comes through these are called implicit. It's buried in the dependence. If we look at the time variation of Q, it will give you the answer, right? So this is called explicit. We considered all of them. We did not. Okay, Euler-Lagrange equations don't change. I mean, whether it is time dependent or not. If it is independent, so this so if there is no explicit dependence on time, then we showed that Q dot dl by dq dot minus L, if necessary, let's put more indices, is conserved. It's a constant of motion. Okay, so now what is your question? I mean, we did look at it.
Sir, I'm asking, since we identified P as dl by dq dot, and we inverted Q dot in
so
terms
from
of
this,
P and
so from this we did a Legendre transform. So let's do that again. So, okay, so we saw that you can go back and forth, do a Legendre transform, and we got H, which is a function of Q of t, P of t, possibly explicit time dependence also. Okay, so all that does is to change, I mean, what you're doing is trading Q dot for P. That's what is happening. All the other variables remain, I mean. So when we looked at the trivial example and the reference, we looked at one function of one variable x, but this L here is a function of three variables, Q, Q dot, and T, right?
Yes.
Okay, so the other two variables Q and T are spectators, so they go through. I mean, they are still there, and they remain. They are there. See, they are there here. Okay, so is that clear?
Yes.
Okay, so let's continue now. Are there any more questions from others? So dynamics is given by Hamilton's equations of motion, not Euler-Lagrange. Okay, and that goes like this. So first thing is, let's just define things. Qi, Pi. So this is point in 2n dimensional phase space. Okay, and then we're given this function which does the time evolution, h of Qi, Pi, possibly time dependent. This is the Hamiltonian. And now let me write the Hamilton's equation. So it says that, what does it say? It says that Qi dot is equal to dh by dpi, and Pi dot, this is all important, minus sign. Okay, so I goes from 1 to 2n. Okay, so we get 2n first order differential equation at the time. So this is what Hamilton's equations does, and it achieved whatever. So the advantage which we saw. So we get this becomes an initial value problem. We can convert it into an initial value problem. . okay, of trajectories in phase space. So this is what we do usually. So let's draw a box. Okay. So let's say that this is our caricature of phase space. Okay, so at 0, suppose the point is here, then we want to work out what it will be at this point, at t equal to 0, and then it will move in some way. So this is like what we did at some later time. Okay, so we don't, but what we do is we give, so at t equal to 0, we say which point it is, which is like saying it's at 0 and pi at 0. And after that, we want to ask how it evolves in time. So this is very different from what we do in the Lagrangian setup usually, where we actually give the initial at the final point in coordinate space. We don't say anything about its momentum or velocity, right? So this is quite different, and this is more natural to the Hamiltonian. Okay, so let's look at observables. Okay, we'll just define observables as a very simple thing. Any function on phase space. So let's say f of q p. Let me write it for one variable real quickly. Okay, so this could be some random arbitrary any function that you can write. You can, I mean, so for instance, it could be something like, you know, f could be, for examples, f could be just, you know, p square upon 2n. Okay, another thing which it could be would be p square upon 2m minus some say qp plus some q power 4, say. This is also, all these are functions like this. We could also make it time dependent, so we could have something which would look like, you know, I keep doing p square, what do I do that? So I can say that it is something like 2 power 4 plus p 2 power 6. So these are all arbitrary functions. You know, here this is explicit time dependence. Okay, so what we want to know, so for observables, so suppose we wanted to measure energy, we would ask what is it you have to do? You have to take the operator for energy, for instance, which is Hamiltonian. So I mean, so suppose, or we could, yeah, let's do one real example, one more thing, which is R cross P. This is also an example of a function of characteristics. So given Hamilton's equations, okay, we can work out the time variation or time evolution of any observable. Okay, and I've defined an observable to be arbitrary function of q, p, and t. Okay, so what is it we want to do? We want to work out what is df by dt. Okay, so this. Okay, so now I'll write it for n variables, n degrees of freedom. So this would have one term, which is the explicit time dependent term, plus okay, so this says that this thing has three kinds of dependencies on time. This is explicit, this is through the coordinate dependence, and this is through the momentum dependence. But now we have something very nice. We know, so we need to use q dot and p dot. So substitute for q dot and p dot in terms of Hamilton's equation. Okay, so what does it say? Qi dot is dH by dP. So we just write again dF by dt equal to partial derivative plus, I'll put a single summation. Okay, so what was it? dF by dqi times dF dH by pi dot, which is a minus, which I've already taken put here. Okay, is this fine? Any questions about this computation?
No, sir.
Okay, so we'll write this. Okay, so this whole object we will define as follows, and PB stands for Poisson bracket. Okay, so you can define this. So any two observables A and B, any two. Okay, I won't keep writing Poisson bracket subscript. Is defined to be, so these are any two observables. Okay. This is defined to be. So they are function from any some 2n dimensional phase space. Okay, so this turns out to be the Poisson bracket of F with the Hamiltonian. Okay, so this is that's a special case of the Poisson bracket. So there is a simplification when F has no explicit time dependence. Why is that? Then dF by dt is 0. The partial derivative, there's no explicit time difference, so the partial derivative to t is 0. Okay, so and this implies that dF by dt is nothing but the Poisson bracket of F with the Hamiltonian. Okay, this is a very, very beautiful formula. And probably the closest we can get to connect to quantum mechanics from within classical mechanics. Okay, so I'll pause here. Is this clear what we have done? Okay, so there are some properties.
In this description, A and B could be also dependent upon time, right?
Not in this equation. Then this equation holds. This is the general. This is general case. And this is true when F has no explicit time. H might have. Okay. Is that clear?
Yes.
So, okay. So now we can discuss, constants of motion. Okay, so we say an observable F is a constant of motion. If dF by dt equal to 0. This we know from before, right? So that means it will not change. Okay, so this implies f equal to constant. Okay, and the value is the same on a trajectory but takes different values. But can differ on distinct trajectories. Okay, but now we have seen that df by dt has these two expressions which I wrote. So case 1 is f has time dependence, explicit time dependence. This implies that df by dt plus the Poisson bracket of f which h equal to 0. Then this term vanishes, so you just get fh equal to 0. Okay, so just a remark or definition. We say that two observables commute, Poisson commute, two observables A and B commute if okay, so here we can see that f is a constant of motion if it Poisson commutes with the Hamiltonian. Okay, is this clear?
Yes.
Okay, so this is something which is a very important idea, but there are also properties of Poisson bracket. Okay, this I won't discuss. It's there in problem set. It's very simple. Please see problem set. That will be discussed tomorrow. Okay, but I just want to discuss three properties. Okay, so let's say A and B are right. First thing is antisymmetric. Again, you exchange A and B, you get this. Okay, so these are two properties, and the last one is a very important one. It's called the Jacobi identity. So here A, B, C are observables. So plus cyclic permutation. So I will just bring B here, then C, B will come here, C will come here, and A will come back here. Okay, so you can do it the other way also. That's up to you. Okay, all these are easy to see, but it's worth understanding it. So here you will see that when you write out these things, you go and just expand all the terms. You will see there will be nice cancellations happening, and it will be zero. Okay, so these are all properties. Okay, so quite often this, for instance, in actual computations, so stuff like this is what we will use. Suppose for instance, if you have some complicated thing, I can break it up. I can write it as A and B, and if suppose A Poisson commutes with C, you will see that the second term drops out. If B Poisson commutes with C, the first term drops out, so that it becomes simpler. Okay, so these are kind of simplifications which we will do regularly. Okay. And there's something which we'll call the canonical Poisson brackets. Okay, again from the definitions you can show this. Qi, Qj equal to Pi, Pj equal to 0, and the only non-vanishing guy is Qi, Pj equal to delta I. Okay, so these are called canonical because the variables Q and P are called canonical. So canonical, I don't know. Okay, these are called canonical Poisson brackets. Involves the basic functions which define phase space. Again, easy to check. Okay. So let's do some practical stuff now. Okay, so let us consider angular momentum. The jth component would be r cross p. So without saying anything, what I mean is there's a particle at position r at momentum p, and this is the definition. The jth component of this will be epsilon j k l. I'll use Einstein's summation convention of xk pl. Okay, so what I want to do now is to do some computations. So first computation I want to do is Lj with say xi. Okay, so then, but Lj is this quantity, so I'll just put it in there. And little thought will show you, I actually didn't show that other property which says that if sum of terms are there, a plus bc equal to ac plus b. So this kind of thing I will use now. So that says I can pull this epsilon, because it's epsilon jkl is just sum over term, so I just pull it out and then write xk pl with xj. So now it is again, we can use that this Poisson bracket, this kind of relation. So, but we look at this, xk with xj is 0. Why is that? It's a canonically conjugate variable, so instead of q, I'm calling it xi xj, which is 0. So I only have to do p with this. So I do that. Epsilon jkl xk, I can pull it out. pl with xj. Okay, now question 2 is, what is pl with xj? Anybody?
Minus delta Lj.
It's equal to minus delta Lj. Why is that? Because the canonical computation relations have coordinate first and momentum later. So xjpl is delta I Lj. So I have to use the antisymmetry of the Poisson bracket, and I get that. So what this says, sum over L is there, so you can replace. So we can just go ahead and plug things in there, and what we will get is minus. This is correct. I made something wrong. I did something wrong. It's not xj, xi. That's what I was wondering. So this just makes it minus epsilon j k, wherever L I get is I, times xk. Okay, and let me just exchange these two, antisymmetry of this thing. So this is equal to epsilon j k ik. Sorry. Yeah, I want to box this and write x Lj with xi is equal to epsilon jik xk. So exercise for you is the following. I'm replacing x with p now, and answer is very interesting. Last one which I will write. What do you think is the answer? Any guesses, anybody?
Delta Gi.
Okay. So this is these are calculations which you can do, but what I want to tell you is that I don't need a calculation. Okay, so this is the story that let's look at L3. Okay, and I'll make a statement which I'll explain. L3 is the generator of rotations about the z-axis. Okay, so let's look at arbitrary rotations and say there's a vector vi prime, vj prime, v2. What is this? v1 prime, v2 prime, v3 prime. So arbitrary rotation with some finite, some angle theta. It does nothing to the z component, right? So this is how a vector transforms, arbitrary vector. Okay, you agree with this? What I've written? This is the definition of vector, right? And so now what I do is I expand this to first order in theta. So I get this is equal to 3 by 3 identity plus order theta squared. Okay, so we can write delta v1 prime is equal to, if you look at this, so delta v1 prime is v1 prime minus v1. Okay, and we'll keep only to order theta, so that will be just this term. It is just theta v2. Delta v2 prime equal to what is this equal to? 0. Okay, so this is what the formula is. Okay, so the statement, all these three statements, so I want to just quickly tell you that all these three statements are just, I'll interpret them as saying xi, x1, x2, x3, or p1, p2, p3, and l1, l2, l3 transform as a vector under rotations. Okay, so that's what I mean. So let's look at this. So I rewrite this as follows. Delta v, this whole combination, there's no prime needed for delta here, so I'll do that. That's the definition. So what we will get is, the general answer is something very pretty. This is equal to theta times where vi can be either xi or pi or li. That's what this statement is. And if you look carefully, that this is what is happening. Okay, so what is happening is that The theta, and you can see that we dropped order theta square term. So here theta is, you think of it as a small parameter, like an epsilon. Okay, so any statement like this is precisely so when we see this, we say, so I made some statement here, right? So we say L3 is the generator of rotations about the z-axis. What does that mean? It just means this. So infinitesimal rotations are generated by this thing, and then there is this whole exponentiation which we can do from group theory, which will tell you the finite case, right? So, for instance, this we should know is equal to e power theta of that same matrix, same 3 by 3 matrix. Here. Exercise, you can check that. Okay, so is this clear? So, example of a second example is H generates time translations. Okay, and for simplicity again, so, and let us ignore explicit time dependencies. In H and observables. So what we get is that, so we already had done something, right? So we saw that in this case, df by dt is equal to the Poisson bracket of f with h. Okay. So we can integrate, you can write this in going back to the first form of the derivative. So we can write this as delta f equal to, okay, f with epsilon h, where epsilon is some time scale, small time increment. So what we are saying is df by dt, we're approximating it by delta f by epsilon, and I took it to the other side. Okay, so you might be slightly bothered. I mean, I could put, yeah. So here you can see that L3 came on the first argument and this thing. So if you want to be consistent, we have to put it in the second argument, say, like here. Okay, but you can see that H is generating, so it's the same story as this. Okay, so more generally, we say that some G of Q and P generates some transformation, right? Some transformation on, say, arbitrary functions of phase space. Some also, I would say, infinitesimal. And the formula is, we'll just copy something which we saw here. Delta F equal to, say, F with epsilon times G. Okay, so this is the general picture that we will have. So we will say that this generates, so on and so forth. Okay, so is this point clear? Okay, so no questions. So let's do a non. Okay, so we'll look at the Kepler problem. In the Hamiltonian setting, we have already seen certain things, but so the first step is to go and write. Okay, so this is carry forward to your problem set. So you can show that, and we saw that it's better to, this is coordinate space. So let's get right. R theta phi, PR, P theta, P phi. So these are your variables in phase space. Okay, so we have tried the Hamiltonian. H turns out to be okay. So exercise to prove this. Okay. Okay. So now, so note that P theta and P phi are not the components of the linear momentum, but they are the momenta canonically conjugate to R theta and phi. Okay. So PR is canonically conjugate to R. So what does that mean? R with PR, what should this be?
Sir, 1.
Similarly, theta with theta is 1. All other things which I am not writing are 0. Phi with P phi equal to 1. Okay. So this is what? Okay. So this is what we get. So first, so I'm going to, so we want to look at constants of motion. Okay. So okay, before we do that, just a quick claim. Claim is that L square, angular momentum square, you can in these variables is P theta square plus P phi square by sine square theta. Coming back here, we know that it's L square. I mean, so this term will become L square upon 2 mu R square. Okay. This is something we knew from the effective 1D potential, etc. This is what we get. Okay. So now we want to work out constants of motion. So first one is energy. Obviously, because I'll do it in a stupid way. HH has to be 0. Okay. Second one is angular momentum. Okay. What does that mean? H with all the components of angular momentum is 0. Okay. So I want to make a remark now. Okay. So angular momentum Li, okay, with any scalar under rotation, scalar function under rotations, what should this be equal to?
0.
Yeah, and that comes back to our picture of saying that it generates angular. So if you take L1 means it will be generating rotations about the x-axis, right? But what is a scalar? So that will tell you how a scalar function, how anything changes. But how does a scalar function change under rotations? Finite also, it doesn't change. So this is that statement. Okay, so the thing is now proving that H with Li equal to 0 is simple, because why is that? Because H, I'll write now in Cartesian form, P square upon 2m, let's do it all in Cartesian, minus K upon R. What is P square? P dot P. Right? So it's a scalar. What is R? So these are both are scalars. So in this active picture of angular momentum generating rotations, there's no computation needed. Okay, but you can check it by hand. So you can go and do this and convince yourself. But I claim that we don't need to do a calculation. Okay, so for instance, more generally, check this also. Li with f of r, any arbitrary function of r should be 0. Okay, so these are things which follow if you think what it does. Okay, so but you can also do the actual calculation and check. And you shouldn't trust all these fancy things. I mean, I always do it even the dirty way. But later I might just show the nice fancy way of doing it. Okay, so third one, which is a surprise, is that there is something called the Laplace Range length vector. Okay, it's a slightly complicated definition, but it's okay. A is defined to be P cross L minus mu K times ER cap is unit vector. So ER cap is unit vector along R. Okay, and this is conserved. Okay, so what do I mean if it is conserved? If we do this, H with AI should be 0 because it has no time dependence, right? So or A with H. Okay, so we will do this computation. It has two parts, so I'll do it in two parts. So I will actually okay, I'll write it the other way. Okay, so let us do this computation. First we will do P cross L. Okay, and let's take the ith component of it. Okay. That's equal to epsilon ijk ek. Okay, sorry, pj. Okay, now that AB with C goes, LK, what do we know about LK with H?
It Poisson commutes.
Okay, it Poisson commutes, right? So it's 0. So we just need to do one calculation. Okay, so we are down to computing only Pj with this thing. But what is H? H is I really want to apologize that there are two Ks. So let me quickly call this L. Okay, so now again Pj with P with P is 0. So this term we don't have to do anything. Okay, I'm jumping steps, but okay. So here's what we need to do. So this is what we have, and so we need to do this computation, but there is something very cute. Okay, so Pj with any function Okay, any function of P and Q. Any, xi and p, arbitrary function. Go back to the actual definitions and do it. You will discover that this is equal to minus df by dx. Just go to the definition and do this. So Pj does this thing. So similarly, you can check Qj with f, same f, will be up to a sign only, it will be the same, but df by d. Okay, so this is now some complicated function, but it just says that it's like P acts like minus gradient of this quantity. This is just epsilon, coming back here, epsilon ijl. There are two minuses, so I get rid of that, plus gradient or di of k by r by. Okay. Why? I put a plus somewhere, but which just means. Okay, you can simplify this, and what do you get? You get Poisson bracket. See, I keep using Poisson brackets. And I apologize, x and r mean the same thing. Oh, that's at the boundary. No wonder it is not working. Okay, sorry, I keep x and r are the same. Okay, is this clear? So now we are done one half. Now what is it we have to do? We have to do the Poisson bracket of xi with h. Okay, again h has two terms. Question 2 is, what is it the second term? What do we need to do with the second term? What does the second term give? So let's come back here. Let's look at this. If you give me arbitrary function of any q's with f, it gives derivative with respect to p of f. But this f here has only dependence on, does no dependence on p. So it is 0. So this term is 0. There are many other ways of seeing it, but I'm just giving you one thing which just makes sense. So now we have to go ahead and we have to do this computation. And I want you to exercise. Do this computation. It's not very hard. Again, we could do it like we could expand this as pj is p square, you write it as pj, and then just use the fact that it acts as a derivative, and quickly you will get the answer. Okay, so I won't do that. Complete. And you may need to use epsilon, delta, or whatever, those kind of things. You complete the calculation and show that. If you combine this implies AI with H is 0. Okay, so let's do some counting now, and so that I can finish. Energy, angular momentum, and Rungelen's vector. So this is one variable 1. These are 3 plus 3, which is 7. What is the dimension of phase space? In this problem, Kepler problem, what is the dimension? If we restricted only to the center, r degrees of freedom, it is 6, right? Forget the center of mass. So that is 6. So it is greater than 6. There's a problem here. The thing is that you cannot have, we cannot have, so in fact, you cannot have more than two n minus 1 degree constants of motion. Okay, so in this case n is 3, so 5, but we have 7. So that's a problem, but then it means that they are not all independent. Okay, so implies all 7 are. So next class I'll ask you this question: why are we saying this? There's a very geometric reason for it. All 7 are not independent. So we need to give two relations. Okay, so I'll give both and stop. A square can also be written little messy, but here. Okay, so I'll end my lecture by just saying that if a system, Hamiltonian system, has 2n minus 1 constants of motion that we can write, then we say it is superintegrable. Integrable means something else, we'll see that. And what we are saying here is that the Kepler problem is integrable in 3 dimensions. Okay, so I'll finish here with a plug for my own work, an article. So see article by Balakrishnan, me, and yes, Lakshmi Bala, in Resonance, maybe last year, where we show that the n-dimensional Kepler problem Okay, so I'll put up this article. It's up to you. It's a fun read, and I enjoyed writing the article, and I also learned a lot because this is not my area of research, and so this was a lot of fun, and so hopefully you will also enjoy reading it. So okay, so let me just stop presenting first. Okay, so any questions? Also stop recording.